Greetings and welcome to Computer Science 221. We're working our way through the instruction set of the LC3. We've learned 3 instructions so far, the AND, the ADD, and the NOT. And we saw that the AND and the ADD had actually 2 different formats to it. Today we have to learn about addressing modes. And this tends to be the topic that folks have the most trouble with. And what's going on here is the following. Remember, there are times where we have to move data from memory to a register. And that's called loading. And then what we have to do is we have to move data from a register to memory. And that's called storing. And the interesting thing is on the LC3, load, there are 4 ways to do this. And for storing, there are 3 ways to do this. And students as well as instructors can find this very complicated, and we'll try to make it as easy as we can. What's kind of nice is that 3 of these correspond to these 3, so they sort of work just opposite each other. And then there's a special case for the load. Anyway, I think what I'm going to try and do is actually have separate videos for each one of these different ways of doing load and store, so you can just sort of focus in on them one at a time. Unfortunately, the most popular one, which is going to be the first one we're going to talk about, is also the one that can cause a lot of confusion. And it's what's known as PC relative addressing. And before I go into the specifics of PC relative addressing, what I'd like to talk about is a program that you've written at some point. Maybe you've written a code in C or C++, or maybe you've written a code in a program in Java. And you know that when you write your program, that basically you can think of your program as sort of looking like this. There's some executable code. And then there's some data. Or if you don't like this picture over here, maybe it actually looks this way. Maybe first there's some data, and then there's some executable code. Doesn't matter. Either picture is going to work in this situation here. But now what I want you to imagine is remember, this thing is sitting out on a disk drive, or it's sitting on some sort of external storage thing. And then what happens is it gets put into memory. And what happens is remember, memory is this big, huge thing. And maybe when it loads this in, it loads it in over here. And here's the data. And here's the executable code. Now maybe when you run the program, maybe when you ran this program today, you weren't listening to your music at the same time. But tomorrow when you run the code, you've got your MP3 player running, and what happens is memory is, so this is today, and here's tomorrow. And when your code gets loaded in, well, now your MP3 player's over here. So now we're going to load your program someplace else, and it comes in over here. And now here's the executable code. And over here's your data. Now the point is that this program is actually living in a different part of memory than it is over here. But yet what happens is we still want your executable code. It needs to be able to access the data. In other words, in your Java program or your C program, when you say A is equal to B plus C, well, remember A, B, and C are just labels for some physical address in memory. And remember, physical address. If we're on the LC3, it's down there and it goes up to that. So these things are actually just symbols or names for physical memory addresses. And so if we look at these different models here, we can see that what's going on is that the physical memory address for A, B, and C is going to be different in this model than it is in this model. Okay? So let's take this a step further. And here's how PC relative addressing works. So think about your program looking like this. And again, here's the picture. And here's data. And maybe over here is A. And maybe over here is B. And maybe over here is C. And up here is the instruction that A is equal to B plus C. Now, remember, we said that this chunk of code and data could reside anywhere in memory, which means that the numbers, the physical addresses that correspond to A, B, and C are going to change. But there is something here that doesn't change. And what doesn't change is the distance between here and here, and the distance between here and here, and the distance between here and there. Okay, this distance doesn't change. Well, how are we going to figure out that distance? Well, there is something that's going to help us out. When this instruction is executing, remember the PC contains this. So if this is at location X, then this is location X plus 1, which means that when this is executing, okay, the PC contains X plus 1. Okay, and it turns out that this, just like these distances here are always going to be fixed no matter where this lives in memory, the distance from here to here, and from here to here, and from here to here is always going to be fixed. And it's that distance that gets stored in the operand, okay, when we do PC relative addressing. So let us look at an example of this. Let's consider a program here. Let's suppose what I want to do is I want to load into R1, and I'm going to say number A. And I want to load into R2, number B. And then what I want to do is I want to let R3 equal R1 plus R2. And then what I want to do is I would like to store R3 at C. And that's the end of the program. Okay, now this is going to take one instruction, this is going to take one instruction, this is going to take one instruction, and this is going to take one instruction. So what I'm going to do over here, I'm just going to kind of think about this program for a minute. I'm going to say, okay, over here, I'm going to load R1 with A. And then I'm going to load R2 with B. And then what I'm going to do is I'm going to let R3 get R1 plus R2. And then I'm going to store R3 at C. Well, that's the end of my program right there. We'll learn later how to gracefully exit programs, but for right now, I want to execute these three statements. So then I go, okay, well, I'll put A right over here, and then I'm going to put B right over there, and then I'm going to put C right over there. And you may recall from some of the programs that we've written already, we can kind of put these programs sort of anywhere we want in memory. It's kind of unrestricted. So I'm going to say, look, I'm going to put this at location 3000, and I'm going to make this 3001, 3002, 3003, 3004, 3005, 3006. Okay? Now, I'm going to come over here, and the load instruction, okay, the PC relative load instruction sometimes has the mnemonic load. And what I want to do is I basically want to load into R1 the value A. And here is what the instruction looks like. First of all, we know that there's 4 bits for the opcode. And the 4 bits here would be 0010. And then I have to specify the destination register, and it's 001. And now, what goes in here, in your book they refer to this as a PC offset 9. Okay? And the reason why it's offset 9 is because there are 9 bits left over. And the way that we are to fill this out is this is a signed integer, and this is supposed to represent the signed distance from the current value of the PC. All right, well, let's think about this. If this particular instruction is living at location 3000, remember when I'm executing this instruction, the PC is going to have the value 3001. Remember, the PC is always one ahead of the current instruction. So it's 3001, and what I want is I want this thing called A. Well, A is at 3004, so if I'm at 3001, I have to go +1, +2, +3. So that is going to be okay. So what this instruction is doing now is it's saying put into register R1 what is ever at the memory location that is at the PC plus this offset. Okay? And this would be at location 3000. This instruction over here is not going to be much different. By the way, before I continue, and I don't want to forget this here, this instruction here is changing a general purpose register, so it is going to set a flag. So for example, if this was a negative number in here, a 16-bit negative number, when I executed this instruction, it would set the negative flag. If this were a 0, it would set the 0 flag. If this were positive, it would set the positive flag. So now I'm going to do this one right over here, and it's going to be 0010, and I want to stick it into R2, 010, with the value B. Now here's the weird part. If you consider when I'm executing this instruction, the PC is at location 3002. And how far is it from 3002 to B? Well, it's 1, 2, 3. It's the same offset as the previous one. Okay, so this is at 3001. And now over here, I'm going to do an add. And I have to look in the back of the book as I'm doing this to see what add is. 0001. And this says add to R3, so that's 011. And I want to add R1, 001. We're in register mode. 00, R2, 010. So this would be at memory location 3002. And now we need a little more space. And let's see if I can keep this all where we can see it. So that's 3002. Now 3003, I need to do a store. Now the format for a store is almost identical. We have an opcode. And then what we have is we have, okay, what register? So we have a source register. And then we have a PC offset 9. Okay, so what's going on over here is we want to store R3, so that's 0011, and we want to store R3, so that's a 011, and we want to store it at C. Well, remember, when I'm executing this statement here, okay, the PC is pointing here, okay, and at this point, now what I want to do is I want to get to C. Well, I just have to add 1, 2. So it's going to be 1, 1, 2, 3, 4, 1, 2, 3, 4. And that's going to be at memory location 3003. Okay, then what happens? Well, I've got to stick some values in 3004 and 3005 for this to be interesting. So if I wanted to, with 3004, I don't know, I could put in hex 0003, and at 3005 I could put in hex 0008, and at 3006 that's where it's going to be stored. Why don't I just zero it out for now? I'll make that a 0, and we'll see what happens. Now what I need to do is I need to convert all of these into hex. So I'm going to come over here, and at 3000, I could enter this in binary. It would just be a mess. Well, this is a 2. 0010 is a 2. And then 0010 is another 2. So that's 0. Then I have 0000. And then I have 0011. At 3001, it looks like I have 0010, and then 0100, so that's a 124, then 0000, 0011. 3002, I have 0001, that is a 1. Then I have 0110, so that's a 2 plus a 4 is a 6. Then I have a 0100, that's a 4. And then I have a 0010, that's a 2. 3003. 0011, that is a 3. 0110 is a 6. 0000 is a 0. 0010 is a 2. Okay, then at 3004, I have 0003. At 3005, I have a 0008. And at 3006, I have a 0000. Look at that. It's a whole program. I'm adding 2 numbers from memory and I'm storing them back into memory. Very cool. Let's go ahead and call up the simulator. Here it is. Right here. We said we were going to do this at memory location 3000. I have to look for my keyboard. It is right here, hex 3123. So I'm going to come over here and I'm going to change it to By the way, look at what it's doing over here. This is sort of confirming that it's doing what I want it to do. Here I'm going to say hex X0000. And there's my program right there. I'm going to execute it. I better make sure that the PC is set to 3000. It currently is not. And why don't I clear all registers? They're all clear. I'm at 3000. And now let's take a look at what's going to happen here. So I'm going to execute the first instruction. Okay, and notice that the first instruction I was going to put into R1, which is at 3004. And notice that R1 now contains the value 3. Notice over here, I am now putting into R2, which is at 3005. So I've got a 3 here and an 8 here. And now I'm about to add them together. Okay, and I should get the answer there. And remember, 3 plus 8 is 11. In hex, that should be a B. By the way, notice that that load set the positive flag. Notice that there's a B over there. And now I'm going to do the store, and it's going to stick it at 3006. So we should see this over here change to a B. And that's exactly what it did. Okay? Now, the thing to notice about this program, the beauty of this program, is that this is, let's see, 1, 2, 3, 4, 5, 6, 7. I could take these 7 words and I can put them anywhere in memory and execute the program. It doesn't have to be at 3000. There is absolutely nothing in here that is dependent upon 3000. You're seeing these 3000s only over here because the simulator is doing calculations for it. But what's really going on is that we really just have offsets from the PC to the thing that we really want to talk about. This is really, really important. This is a major, major feature of PC relative addressing, which is the idea that code is relocatable. I'm going to write that down. because this is certainly a great quiz question. PC relative addressing permits relocatable code. Okay, and I'll put an asterisk here, and the asterisk means executable code can reside anywhere in memory. And that's really, really, really powerful feature. And no, not all CPUs can do that. Many can, but not all of them. The LC3 can do it. Now, before we wrap this up, I just want you to think about a couple of things here. If I'm doing PC relative addressing, how does this work? For example, suppose I'm doing an LD. Well, if I'm doing an LD, so here is the instruction register. And if I'm doing an LD, there's a 0010 in here. And then there is a register specified. And then over here, there are 9 bits. Okay? And the first thing I have to do is I have to take these 9 bits and I have to send them to a sign extension register. Okay? Then what I have to do is I have to take this and put this into the ALU. Okay, and what goes in the other side here? The other side here is the PC. This is the ALU. And what I have to do is I have to give it the control signal to add. Okay, what comes out of here now has to go into the MAR. Okay, the MAR now goes into memory. We select the thing that we want. That now goes into the MDR. Okay, and then ultimately this has to go into the register. So there are a lot of steps going on in here. The thing to recognize here is that to go ahead and do this thing is we have to do this add over here, okay, with these 9 bits and the PC. That add takes time. Later on, actually, when we talk about some other ways of doing things, we're going to see that some addressing schemes don't use PC relative addressing, and we cut out the add step. Now, there are pros and cons to this. The pro to it is by cutting out the add step, it's going to be faster. This takes time to do this. The con to it is going to be that we're limited in what we can do. Now, there's something here that we need to think about. I've got 9 bits here. I've got a 9-bit signed number. So the question is what is the largest 9-bit signed number? Well, that would be this, 1, 2, 3, 4, 1, 2, 3, 4. Okay? And the question is what number is that? 1, 2, 4, 8, 16, 32, 64, 128. So this is 255. So of course, if I calculate the 2's complement of this, I get 1, 1, 2, 3, 4, 1, 2, 3, and then there'd be a 0 and I'd add a 1. That's minus 255. So what that means, and again, very important point and something that will certainly show up on a test or a quiz or something, is that if I've got an instruction here, okay, and this instruction is a load, so remember, if it's a load, the PC is over here, I can only go back this way, 255, and I can only go this way, 255. Okay? In other words, I can only do a load into here that is at most 255 in either direction from the instruction right after it. Well, you might think that's a limitation, and it certainly is a limitation, which means that we must have some other addressing modes at our disposal if we want to be able to address the entire address space of the computer. And that, my friends, will occur in a different tape. Okay, bye-bye.